Okay, welcome to day 3. We're going to talk about radians. Radians are a very important part of mathematics. In fact, any course beyond this, you never really talk degrees. Everything's in radians. So radians are not going to go away, and we'll talk about why radians are actually a better way to talk about things than degrees. We're going to talk about arc length and area sector. So what is a radian? A radian is a central angle made up by taking a radius and wrapping around the perimeter of a circle. So I'm going to move this up. A radian. So the idea is that this is a radius. This red is a radius. And this is 1 radian because the red radius line is the same length as this arc length. We'll talk about arc length later. Has the same length as 1 radius, and that's the idea. Is that this red line radius is equal to the same length as this arc or perimeter length, except it's curved. So that's called 1 radian. So we call this angle theta is equal to 1 radian because it's exactly the same length as 1 radius. So how many radians does it take to go around the circumference of the circle? Well, this guy is equal to 1. If I do another length, maybe here, that's about 2. Maybe here is another length. That's about 3. It's maybe a little bit short of the mid semicircle. Another length. Maybe that's 4. Another length. Maybe that's 5. You know, this is all to the best of my ability. And this last one, again, a little bit short of a full circle. I say about 6. About 6 of those radians will go all the way around a circle. So let's talk about this. One revolution around the circle is 360 degrees. And if you recall from geometry class, the circumference of a circle is 2 pi times the radius. And on the unit circle, the radius is equal to 1, so if I plug 1 in there, the circumference of a unit circle is 2 pi radians, or 6.28 radians. That's why this is a little bit short. It takes 6.28 radians. The reason why we talk about radians being better than degrees is because degree is kind of like opening up a door so many degrees. It's like a wedge opening. Radians is actually a perimeter length or an arc length on the circle, something we can measure as a length. So again, one circle is 360 degrees, or 2 pi radians, or a half a circle, semicircle, is 180 degrees, which is pi radians. I'm going to use this guy to be my conversion factor. So when we go from degrees to radians, I take my degrees, I multiply by pi, and I divide it by 180. Okay? And that will give me my radians. And usually what happens, I don't worry about the pi when I do this. I'm going to get some numerator times pi over denominator. I'm usually going to get a fraction with pi involved. When I want to go the other way around, convert radians to degrees, I take my radians, which is usually some n pi over d, and I'm going to multiply it by 180 degrees over pi, and I kind of get my pi's that cancel out, and what I really get is n times 180 over a denominator, and that would be how many degrees I have. It's really not that tough. You can use your calculator a little bit, but some of the math is pretty easy. As an example, 30 degrees. So I do 30 degrees, I multiply by pi, I divide by 180, because I'm using the one I did in pink. 30 over 180 cancel out to 1/6, so I get 1 pi over 6. I don't even need to include the 1. To go the other way around, I do pi over 4. I'm going to multiply by 180 over pi. I get the pi's that cancel. I get 180 over 4, which is just 45 degrees. So which is bigger, 1 radian or 1 degree? Well, I don't even know if I can draw 1 degree. I'll try my best. But 1 degree would be really long, barely up, and like that. I bet you even that's bigger than 1 degree. 1 radian, if this is a radius length, I have to draw an arc that's about the same radius length. And this is 1 radian. So 1 radian is a lot bigger than 1 degree. In fact, if I do the conversion, 1 radian times 180 degrees over pi, I get about 57.3 degrees. So a little bit less than 60, a little bit less than 1/6 of a circle. That's why it takes a little bit more than 6 of them to complete a circle. Okay, I'm going to complete this whole big picture. I'm probably going to turn the camera off, the video off many times to do it, but let's do a degree. So I know this one at the beginning, the positive x-axis is 0, and I'm going to count the ones in the middle of the quadrants are 45 degrees. So 45 degrees, 90, 135, 180 degrees, 225 degrees, 270 degrees, 315 degrees, and finally 360 degrees. That's by 45s, and I could do by 30s, so 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150 degrees, 180, 210, 240, 270, 300, 330, wow, that's not 330, 330 degrees, and 360 degrees. So those are the angles in degrees. We also know that every xy on this unit circle is cosine theta sine theta, and we've done this enough that we can go ahead and do quadrant 1. Show all the points on quadrant 1. This is 1, 0. This is radical 3 over 2, 1/2. This is radical 2 over 2, radical 2 over 2 at 45 degrees. This is 1/2, kind of radical 3 over 2. And the point up here is 0, 1. And that is quadrant 1. I'm going to use that quadrant 1 idea that I've done many times. I'm going to apply that whole all students, I'll even do it here in red. All, well, it'd be nice if I did it right. All students take calculus. And I can figure out the other 3 quadrants in the same ordered pairs that I have up here in quadrant 1, except some are positive, some are negative, depending what quadrant you're in, and so on and so forth. I also know that tangent of theta is equal to sine of theta over cosine of theta, which is y over x. So tangent is just the slope of everything. So I'm going to do the slopes in quadrant 1. So right here, the slope in quadrant 1, this slope is 0. The slope in the middle right here is 1. So this one's smaller than 1, like 1 over radical 3. This slope here is bigger than 1, like radical 3. And this slope here at 90 degrees is undefined. That we know. So again, I have this whole quadrant 1 picture. I'm going to apply my all students take calculus to all other 4 quadrants, and I'm going to fill in that picture right now. So now you can see I have filled in for all the order pairs, all the angles and degrees, and all the slopes or the tangents in pink. Now I'm going to do the radians. And again, the idea of the radians, I should be able to figure this out, but this radian here is 0 radians. 30 degrees, I think we did on the previous page, that was pi over 6. The previous page we also did this was pi over 4. This turns out to be pi over 3. This turns out to be pi over 2. So what we're going to do, I'm going to count around the circle in pi over 6s. Or pi over 4s, all the ones that are in the middle. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is halfway around the circle. 5 pi over 4 is in the middle here. 6 pi over 4, which is down here, which is 3 pi over 2. This is 7 pi over 4 in the middle. And this is 8 pi over 4, or 2 pi, which we know is all the way around the circle. Now I'm going to count over in pi over 6s, which is not in the middle of each quadrant, right before and right after. So 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6 reduced, 5 pi over 6 reduced, 6 pi over 6, 7 pi over 6, 8 pi over 6 reduced, 9 pi over 6, 10 pi over 6, and this last one is 11 pi over 6. And that is our whole big picture in degrees, radians, x and y cosine sine values, and slope tangent values. So how to develop this whole big picture without memorizing the whole thing? Well, we talk about these reference angles. We talked about them the other day with degrees, and I'm going to do them with radians. And actually radians is going to be a lot easier. You're going to like the radians because it's really just based off the denominator. Now, it's the same picture I had before, depending on what the 4 quadrants are, and so on and so forth. But we talked about this little shortcut way of looking at things. And we talked about for degrees, if it was on the x-axis and divisible by 90, it was 0 degrees. If it's on the y-axis, it was 90 degrees. Ends with 5 was 45 degrees. Divisible by 60 was 60 degrees. And if it was none of these above, it was 30 degrees. And that's what we have on this whole big picture up here when we did that table. Well, today is actually going to be easier because all I have to do is use these angles. These are the ones in quadrant 1, and that's quadrant 1 right here. And the quadrant 1 angle is always pi over denominator. And you notice the denominators get smaller as I move through the quadrant. And every other quadrant, the angle looks like this. A numerator times pi over a denominator every single time. And the pattern is, when you're in quadrant 2, the numerator is 1 less than the denominator. When you're in quadrant 3, the numerator is 1 more than the denominator. And when you're in quadrant 4, the numerator is equal to 2 times the denominator minus 1. And that's how I figured out all these little things. So when I want to figure out 7 pi over 6, 7 pi over 6 its reference is going to be pi over 6. I only have to look at the denominator. And 7 pi over 6, and 7 is one bigger than 6, it is in quadrant 3. So this is the exact same table we did the other day, except we're going to add radians to this. Figure out what are all the radians for all this. So quadrant 1 is pretty easy. We've done it many times. It's the only one I really know. I really don't know part of quadrant 1 because I could duplicate the rest, because if one of them is 1/2, the other one's radical of 3 over 2, and vice versa. And one of them is 0, the other one is 1, and vice versa. So every time I'm in quadrant 1, these angles are the reference, and every angle is pi over denominator. So let's move to quadrant 2. So when I move to quadrant 2, these are going to be the exact same results. Nothing's going to be changed. So I'm going to be in quadrant 2. Only the sign is going to be positive, and we'll get there. And every one is going to look like n pi over d, where the numerator is 1 less than the denominator. So to me, these angles are going to be 2 pi over 3, 3 pi over 4, 5 pi over 6, and so on and so forth. And this one is just pi. Same reference, 60, 45, 30, 0. Well, 60 is pi over 3, this is pi over 4, this is pi over 2, and this is 0 as its reference, and you're going to use the same values as before at pi over 3 or 60, radical 3 over 2, 1/2, radical 3, 2 over radical 3, 2, 1 over radical 3, except when I'm in quadrant 2, only the signs are positive. So positive, negative, negative, positive cosecant, negative, negative. So I've done the same thing for the rest and realized I have to make all the cosines and the tangents negative, and I have to do the same thing for the secants and the cotangents. Make them all negative. So I'll go on to quadrant 3. Quadrant 3 ends here at 270. This is where my tangents are going to be positive, and this time my fractions are going to be, my numerator is going to be 1 more than the denominator. So if I look at this carefully, 210 is a 30 degree, 45 degree, 60 degree, 90 degrees, and according to my, this is pi over 6, pi over 4, pi over 3, pi over 2, except my actual angle, my numerator has to be 1 more. So 7 pi over 6, 5 pi over 4, 4 pi over 3, and 3 pi over 2. And I could fill in the rest for the sine, cosine, tangent, cosecant, secant, cotangent values. And because I'm in quadrant 3, the tangents are positive. These are the third column. So sines are negative, cosines are negative. That means cosecants are negative, secants are negative, and I don't have to do the zeros on undefined. And then I'm going to move to quadrant 4, which will start off in purple. This is quadrant 4. This is where cosine is positive, and all the numerators are going to be 2 times the denominator minus 1. So this reference is 60, 45, 30, and 0, or pi over 3, pi over 4, pi over 6, and then finally 0. And so 2 times that, 2 times the denominator, or 3 minus 1 is 5 pi over 3, 7 pi over 4, 11 pi over 6, and then finally 2 pi. And again, I can fill in the rest of the table based on what I did on the earlier part. And in quadrant 4, the cosine is positive, so all the sines have to be negative, all the tangents have to be negative, cosines stay positive, and that means cosecants have to be negative, and the cotangents have to be negative. And we don't switch to zeros and undefineds. Okay, there is a table. So when we talk about the unit circle, we have some nice things. First of all, we know that every xy is just equal to cosine of theta, sine of theta, where this is the theta right here. Another thing we have is that this arc length is equal to whatever the angle is if their angle is given in radians. As an example, if we said that this central angle of this red arc is equal to 30 degrees when we use the opening here of 30 degrees, this arc length in red is equal to pi over 6 radians. And that's actually a better way to talk about degrees because it is a physical length, where 30 degrees is just some opening of a wedge. It's hard to figure that out, but I can actually measure that length. So radians is the way to go. So this arc length on the unit circle, arc length is just equal to that angle when theta is in radians. So we're going to use radians more and more and more. Well, how about if I don't have a unit circle? How about when I have something that is not a radius of 1? I could have any radius. Well, my principles for cosine and sine still hold out, that cosine of an angle is equal to adjacent x over the hypotenuse r, or x equals r times cosine theta, and then y, sine of theta is opposite over hypotenuse. So y is equal to r times sine of theta, and I have these two formulas right here. So really what I have is every point on the circle is still cosine theta, sine theta, except now we're going to multiply them by the radius r to figure out what the real values are. So I have two examples. One we have to use our calculator, one we do not. I have a radius of 5 and an angle of 80 degrees, which I know is in quadrant 1. So x is equal to 5 times cosine of 80 degrees, and y equals 5 times sine of 80 degrees. I have no idea what those values are without a calculator. So my point is going to be 0.868, 4.924. Those would be the x and y values on the circle of radius 5 with a point at 80 degrees. And again, positive, positive is in quadrant 1. Next example, I have a radius of 8 and an angle of 4 pi over 3. Since the numerator is 1 more than the denominator, I know that is quadrant 3. It's in radians. So I'm going to have to use some exact values. So x is equal to 8 times cosine of 4 pi over 3, and y is equal to 8 times sine of 4 pi over 3. Now if I think about this, 4 pi over 3, that's really just pi over 3, or 60 degrees, and cosine of 60 degrees is 1/2, but we're in quadrant 3, so that's going to be negative 1/2. So I get negative 4 as a result. So if one of them is a half, this sine value has to be radical 3 over 2 because they go together. Again, it's in quadrant 3, so it's negative. I divide by the 2. I get this as my result. Negative 4, radical 3 is my result, and that is in quadrant 3. It should match negative, negative. So now I want to figure out this arc length, because arc length is easy when I have a unit circle. The arc length is just theta in radians. So I want to figure out this arc length on a circle with any radius, or to me, if I think this circle is a big pizza, this is the crust of the pizza. How long is that crust? Well, it's exactly what we did before. When we went to figure out x's and y's, we have to multiply these values by r to figure out our x and y's. Well, I'm going to do the same thing. The arc length formula is just going to be theta, but I have to multiply by r, and I have to make sure that theta is in radians. It must be in radians. You cannot use degrees or anything else. Theta must be in radians. So let's go through some examples. Let's go through the easy example. So I want to figure out this arc length of an angle 4 pi over 3 on radius of 6 inches. Well, here's my radius of 6. Look at this theta. This theta is in radians. Makes my life easier. I don't have to do anything with it. So I'm trying to figure out this arc length. Remember, 4 pi over 3 we said was in quadrant 3. So from here to here, I'm trying to figure out this arc length. Well, my arc length is equal to my radius of 6 times my angle of 4 pi over 3. I get 8 pi. Don't forget your unit. In this case, it is inches. The next example isn't so easy because I have an angle of 150 degrees. I can't use that. I have to convert 150 degrees into radians. So I have to multiply by pi, divide by 180. I get theta is 5 pi over 6. And that's the theta I have to use. I cannot use degrees. So I converted my 150 degrees to 5 pi over 6 radians. I have a radius of 5, so I'm trying to figure out this arc length. So L equals 5 times my radians of 5 pi over 6. I get 25 pi over 6. The units are feet. That is the length of that arc. In this last example, a little bit different. I have a hand moving on a clock. I have 50 minutes. Well, I know 1 revolution of a clock is equal to 2 pi for a circle is equal to 60 minutes. So I have to do my theta is equal to 50 minutes times a conversion of 2 pi over 60 minutes. I get theta is equal to, let's see, I get 100 pi over 60, and I reduce that to 5 pi over 3. That's the theta I have to use. I cannot use 50. So I drew my clock. I have a radius of 12. I'm trying to figure out this arc length. So L is equal to radius of 12 times 5 pi over 3 is my theta. I can't use 50. I get 20 pi inches as my result. That's how far the minute hand would travel if you had a minute hand that was 12 inches long. So in the previous page we were figuring out arc length, or what I would call the length of the crust of a pizza. Sector is area. This shaded area, this is a sector. And that's actually the size of the slice of pizza. So here's the formula for the sector. And again, theta must be in radians. So area equals 1/2 theta r squared. It's an area, so something is going to have to be squared in it. And I'm going to do the exact same three problems as I did earlier, except now I'm going to figure out the sector area instead of the arc length. So I'm lucky that this one is given to me with theta was already in radians, so I could do A equals 1/2 4 pi over 3 times my radius squared. 36 divided by 3 is 12, divided by 2 is 6, times that is 24 pi square inches. Don't forget your units. So since this is the same problem as the previous page, except now I'm figuring out the area of the sector, I don't have to go through the whole process of converting it. I already converted the 5 pi over 6 on the previous page, so A equals 1/2 5 pi over 6 of theta times my radius squared. I get 5 squared times 5 is 125 pi over 12 square feet is how big that sector is going to be. So again, going back to the same problem with the clock, I already converted to 5 pi over 3 for my theta. So my area is going to be 1/2 5 pi over 3 times 12 squared. And I do all the arithmetic. I get 120 pi square inches is the area of that pink sector. Okay, thank you for watching this video.